Anyway, I'm Gilad, and I want to welcome everyone. Good morning or good afternoon, wherever you guys are, or good evening. So Pasha told me that we created UCF 9 years ago. 9 years ago. The main reason to create the UCF Consortium was to host open source collaboration projects and be able to protect them. So they're going to remain open source and they're going to remain collaboration projects. So we established the UCF Consortium. The first project was UCX, which obviously continues. And then down the road, we added several other projects, including UCC for collective operations. And I'm checking with Manju if Manju can give us an update this week as well. There is a work group around benchmarks, and there is a work group around creating services for smart NICs or DPUs or IPUs or whatever you call those items, but essentially NICs that has compute engines on them. At Supercomputing 2 weeks ago, the folks from Barcelona Supercomputing Center presented their contribution of having OpenMP runs on DPUs. The code is now under UCF GitHub. So if anyone is interested, the code is there. And they will be continuing developing services for DPUs as part of that working group. Since we're a little bit over time, starting this morning, we wanted before we start with the first session, we wanted to take a group picture. So we'll utilize or use the break here at around 11 a.m. give or take to take a local picture. But if you guys on the other side that connected remotely are willing to open your cameras, then we can take a screenshot, and then Pasha will do his magic and combine those two pictures together. So we'll fill all together. So last call, anyone that has a camera that is willing to open it, and we're going to count to 3, and then John's going to take a screenshot. Okay, 1, 2, and 3. Thank you very much, guys. Do you have it? Cool. So you will have some work to do after that. The first session, you want to use?
Yeah, I want to take a couple.
Oh, here you go.
I want to use the opportunity to thank actually organizers of this face-to-face workshop. This event, it's actually usually a lot of work. I don't know if we have Oscar. I see Oscar online, so I want to thank Oscar for helping in organizing all this online website, driving easy share for registration, for submissions, reviewing in all the processes. So it's a lot of work. Thank you, Oscar. As well, I want to thank all the board members for driving reviews. Obviously, I want to thank John for hosting us at ARM, almost as usual. Every year we meet here in Austin at ARM. And thank you for your sponsorship, guys, for the facilities, for foods, for being excellent hosts. Like really appreciate it. And you have been doing this for many years as well, so we're really thankful. I want to thank Brian Sparks from NVIDIA as well that helped to organize again all the online activities and social media and so on. It was super helpful. I hope I don't miss anybody. I want to thank all the people that submitted talks and arrived here. We really appreciate it. I know it's like these days, travel is not easy, so really thankful for these guys. And obviously for all the online attendees across multiple time zones, thank you for joining and making time for this. Really appreciate it.
You want to first one?
Yeah, I can announce. So our first presentation is by Edgar Gabriel. Edgar is here. He will present recent advancements in UCX for AMD GPUs.
Am I presenting from
Yeah.
machine?
From your machine.
From your machine.
Do I need to log in to the online session in that case, or how does it work?
Yes. And you will be like musician with mic and everything.
Yeah.
And I want to apologize this morning for all the delays, guys. We, again, as usual, struggle with Zoom and mics and everything. We have this every year. This is part of tradition as well. And yes, this our, as Gabriel gets online, this is our 9th workshop. Actually, we had first official workshop was in the basement of UTK University in Knoxville, Tennessee, a while ago. We had one unofficial workshop with just few of us in Oak Ridge behind the fence. It was a while ago as well, when we just conceived the idea of having this workshop in UTK. So this is exciting, a lot of time passed and a lot of good work happened in these years.
So good morning, everybody. Thank you very much for the kind introduction. So what I want to do over the next couple of minutes is just present some of the work that we've been doing over the last year and some of the things that we've been working on more recently. And from the high-level perspective, I mean, I'll probably spend the first 2-3 minutes to set a little bit the stage in terms of what is the current support for ROCm devices in UCX before I focus then mostly on some of the new features that we added to UCX 1.15 that was released earlier this year. I will also spend a little time on showing or presenting some of the issues that we are working on for with respect to the V2 protocols that is relevant for, I think, UCX 1.16. Yeah. And the final part of the talk will then focus on something not related to our GPUs, namely some work by one of my colleagues to improve data transfers for some of the new Zen 3 and Zen 4 architectures in UCX. So, but let us get started with just a couple of minutes talking about what is the current support for ROCm devices in UCX. So our devices were supported in UCX actually quite some time meanwhile, and the fundamental building blocks that are there are a component that enables data transfer between GPUs and CPUs. That's the ROCm copy component. We have then a transport that basically supports data transfer between two GPUs directly. That's the ROCm IPC component. And although not part of the UCX distribution itself, but a key element to make things work smoothly is the necessity for the kernel component, the ROCm RDMA component that basically enables an RDMA capable device to fetch directly data from GPU memory if conditions are right, if things work. So these are, in my opinion, the 3 most important aspects to make things work in a performant manner. You do need some additional support for various other functionality, including, for example, detecting ROCm memory in UCX or the memory hooks that allow to intercept ROCm memory allocations. If you look at the bigger picture, and we look at, let's say, how this is utilized from within OpenMPI. So OpenMPI internally is organized in the so-called frameworks, each framework supporting one particular aspect of the functionality. So for example, the PML framework implements the fundamental messaging or data exchange operations, MPI send, MPI receive, right? So within this context, I mean, the PML UCX is basically the main PML component that we use at the moment for our devices. You can also utilize the OSC UCX component for one-sided operations, right? Starting from OpenMPI 5.0, we introduced the accelerator framework in OpenMPI, and we have in the accelerator framework also a ROCm component. That component is basically necessary for some pack-unpack operations, but also for some of the operations that occur in OpenMPI, maybe outside of UCX, right? So it's still a key part of the overall software architecture and picture. And last but not least, also of relevance, I think, for this particular workshop, So for collective operations, especially for reduction operations, the most performant component that we have at the moment is the UCC component. So UCC introduced also support for ROCm devices starting from release 1.1. It can utilize both the UCX-based UCP team layer component, which basically implements collective operations on top of like point-to-point exchanges, etc. But it can also launch like a GPU kernel for reduction operations to make things performant, right? UCC internally then can also sit on top of RICL. However, the ROCm collective communication library that basically executes GPU-based collective operations directly. So as a big picture, this is probably at the moment our most stable, best tested, and best performant configuration for MPI applications. Now, let me spend a couple of minutes on some of the new things that were introduced in UCX 115. First one, we basically introduced for the ROCm copy transport, the ability to execute asynchronous copy operations. And what this really gives us is that for device to host transfers, this allows to overlap some of the stages of the pipeline overall. So if you compare using, let's say, OSU benchmarks, where one process has memory in host, where one process operates on host memory, the other one operates on GPU memory. If you compare UCX 1.14 and 1.15 with this new feature, you see that basically this asynchronous handling of the data exchange basically allows us to improve the performance by around 30%, right? A side effect, and probably more of interest to the developers than the larger community. So when we did this work, we also like abstracted out the progress operations of the ROCm copy and the ROCm IPC transports into a single function. This allows us basically to simplify code maintenance and management. Second new feature was adding support for DMA buff in UCX for ROCm devices. So as I mentioned previously, if you have RDMA capable network devices, at the moment most configurations utilize a kernel component in order to perform the memory registration of GPU memory that allows basically afterwards the NIC or the HCA to access data directly from the GPU. DMA buff is an alternative mechanism that is basically supported by the Linux kernel subsystem to share GPU buffers across multiple devices, right? I think DMA buff support in the Linux kernel is there for quite some time, but basically over the last few years, this also has gained momentum in utilizing it in UCX and in other communication libraries. Long term, I think many of our developers see that as a replacement for the kernel component. High level perspective, in my opinion, it works. I'm not yet sure whether we are there that we can completely ditch, however, the kernel component at the moment. ROCm release 5.6, which was released, I think in May last year, introduced the ability to export a DMA buff handle from the ROCm software stack, right? So this was basically the foundation for this part of the work. And from the high level perspective, again, things that are required in order to support DMA buff for ROCm devices. So you need a ROCm version that basically has the functionality to export a GPU buffer. Again, this is available since ROCm 5.6. You need a version of the libib verbs that is able to import a DMA buff handle, right? So basically you need the IBV-reg DMA buff MR functionality. And last but not least, at least for our devices, we need to make sure that the kernel has certain configuration parameters enabled. Without that, it's actually quite tricky because the DMA buff seems to work, except that some of the subsequent operations for IPC exchange might fail, right? So all of these three components are, however, at this point in place. And if we compare, let's say, performance-wise, what you can achieve in UCX 115 with DMA buff versus the kernel component, bandwidth-wise, not much of a surprise. It is not a significant difference or no difference at all, let's put it this way, right? Whether you use DMA buff or the kernel component for the data exchange. Latency-wise, we see a tiny little bit of difference, although I'm not entirely sure whether it's just noise in the measurement versus actual, whether that's an actual impact. But let's put it this way, 8 out of 10 runs, you see a tiny increase in the latency when using the DMA buff registration mechanism compared to the kernel component, which is interesting because if you look at the actual time spent in the various registration mechanisms, DMA buff based registration seems to be on average for most message lengths significantly faster than the kernel based method. Now, this measurement might have some flaws, but it's just simply measuring the time that is actually spent in IBV reg MR versus IBV reg DMA buff MR. But conceptually, think of it just this way. At the moment, the exporting the data handle seems to be virtually a no-cost operation, very cheap. The registration itself, up to message lengths of I don't know, something like 16 or 32 megabytes. DMA buff-based registration seems to be faster. For very large messages, however, we see for whatever reason the cost of DMA buff-based registration goes significantly up. Honestly, not sure what that is, what that is based on, yeah, or what triggers that behavior, whether it's something in IB verbs or in our ROCm devices or in some of the exchange mechanism. Some two more smaller features that I wanted to simply bring up. So we revamped the code in UCX 115 on how we set a device ID for AMD GPUs. Again, users will probably not notice that, but basically this should enable for more accurate distance calculations for some of the protocols. And we also changed the logic on how GPUs are assigned for the ROCm memory domain. And the tricky part there is that the ROCm support in UCX is based on the ROCm runtime functionality, the HSA functions. And that function has no knowledge of what is the current device. So if the user calls in an application hip set device, that has no meaning whatsoever on the runtime layer, right? So determining which GPU the user intended to use is actually, because of that, quite tricky to determine. We are able to set the GPU if we had the ability to intercept a hipmalloc function call, because in that case we can check which GPU was used. We can parse environment variables such as hip visible devices, but we are only using this information if the user only set one device on hip visible devices, right? Which I know that some of our customers do based on some shell scripts that they use when they launch an application. All right, few words, V2 protocols, on V2 protocols. So I think we made some significant progress over the last couple of weeks from that perspective. So correctness-wise, I think we seem to be good at this point in time. We don't have any errors showing up or popping up anymore. Intranode, internode. Intranode performance, if we look at, let's say, the performance of point-to-point operations with OSU benchmarks, we are actually at this point better than we were with 1.15 with the original V1 protocols. Because of that, we're a bit surprised, and we are still investigating what is causing that. If we look at like a larger communication pattern, however, we still have some overhead compared to the V1 protocols, right? So point-to-point looks good. Collectives, we seem to still have some issues that we need to hunt down to see why we see some overhead. Internode performance-wise, I mean, Rocky and IB networks were both tested. Point-to-point-wise, I think we look mostly good. It's, I think, not quite as smooth yet, the graph, as what we had previously in with the V1 protocols, but we are in the same range. For the collectives, I think we have a somewhat similar behavior, although not quite as significant difference-wise for GPU buffers, what we see for intra-node collectives. So bottom line is, I think we're getting there. A little bit more tuning work and is required from that perspective. All right, so last part of my talk. I'm way too fast. Are there any questions? All right, so last part of my talk is the work performed by my colleague Arun Chandran on improving the performance of shared memory communication in UCX for some of our newer architectures based on non-temporal buffer transfers. And from the high-level perspective, what the situation or the scenario that we're really targeting are the new Zen 3 and Zen 4 cores that have been released over the last 1 or 2 years. Typically, the way these architectures are organized is that you always have a group of cores that share a level 3 buffer, right? And now an application, let's say an MPI plus OpenMP application, what it would very often do is basically you launch one process on one of these groups of cores and use all of the cores within that subgroup using, let's say, OpenMP threads, right? Now, from the optimization perspective, basically what we need to target are 2 different scenarios. One is copy in, copy out scenarios for shared memory protocols, and one is single copy mechanisms, data transfer mechanisms, right? And I'll say a few words to both of them. If there are in-depth questions to that, Arun is, I think, online, and he's here to assist with technical questions that I cannot answer. So the key goal, let's talk first about copy in and copy out mechanism. So the key goal really is that we use copy operations that basically bypass the level 3 cache. So we have 2 different mechanisms that we use instead of regular memcopy operations. In that case, we use a non-temporal store for the copy in operation that again bypasses the level 3 cache, and we use a load with prefetch instead of the regular load operation in a copy in, copy out scenario. And from the advantages perspective again, so this reduces the data transfer latency by circumventing cache-to-cache updates, right? So that is the first aspect. The second aspect is that because we bypass the cache, it also reduces cache pollution overall. Now, if you put these things together and you evaluate the performance of a copy-in, copy-out protocol, again, using OSU latency, you see that there's quite a significant performance benefit on both Zen 3 and Zen 4 architectures, right? So for 128 kilobyte messages on Zen 3, we get a performance improvement of up to 43%, and on a Zen 4 architecture of up to 28%. So that is quite significant. The second scenario, single copy operations. So there we are focusing in this part of the work on XPMEM, because that's the only single copy mechanism that uses memcopy internally for the actual data transfer. And similarly to what was done for the copy in, copy out mechanism, we basically replaced the memcopy by a load with prefetch in this particular scenario. And again, benefits are overall the same in terms of that you reduce cache pollution and you can potentially improve the performance of that operation by bypassing the cache. Performance benefits, again, if you use OSU latency for as a benchmark scenario, the performance benefits in this particular scenario are somewhere between 5 to 7% for larger message sizes on a Zen 3 architecture, and somewhere in the range of 4 to 5% for Zen 4 architectures. So this work is currently still in progress. I know that my colleague has had has some additional work lined up there and some pull requests pending to UCX. So we hope to get it into UCX very soon and then, yeah, evaluate it for larger scale applications. All right, so to summarize, well, the disclaimer is not the important part. To summarize, so I think we, again, UCX for us, I think at the moment is by far the best and most stable configuration that we can use for our GPUs. We've invested significant work and efforts into improving our GPUs, improving the support for our GPUs, both performance-wise and functionality-wise. There are a couple of other items that are also pending that we are still working on. Some of them will probably make it into UCX, some of them might not. We'll have to see. But yeah, anyway, that's all I had to say. Thank you for your attention. And if there are any questions, I'm more than happy to answer them. Yes.
Actually, I have some question about the non-temporal stuff.
We may need to pass the mic around.
Essentially,
thanks. So from what I understand, the benefit for non-temporal move essentially would be like cross NUMA or between the cores that doesn't share a L3 cache, right? So you bypass the local write to your local cache. So in that case, if the two processors are actually on the same CCS, then we should still be using the regular move.
I think so. So that's why I think my colleague also has designed this feature as an opt-in.
Mm-hmm.
So that basically you have to explicitly turn it on if you want to use this
Okay.
feature.
Yeah, because I only mentioned because I've been testing this on MPitch recently. Basically, for across NUMA communication, this non-temporal move is significantly beneficial. But on the within the same NUMA, it's actually not adding. It's adding some overhead. So the ideal not using that in that case. A second thing is I look at the PR. It's implementing using the AVX instruction, right? The non-temporal move is using the vectorized version, the AVX 256 instructions. So I was wondering, have you guys tried the non-vectorized version that in the SSE instruction set?
I think in that case, I need to ask Arun whether he can answer that question.
Oh, okay.
Yeah, can you hear me?
Yes.
Yeah, we are not tried yet. So we have tried only with AVX2 as of now. But why is that question? Or why do you see any special reason for using SSE2?
Sorry, I couldn't hear clearly. There's some echo.
Okay. So currently we are using AVX2 instructions only.
Mm-hmm. Okay.
So I just want to ask you why you are specific about SSE2? Do you see any special benefit for that?
No, I was just curious because if AVX is not supported, then basically I need a fallback solution. And I realized there's also a non-AVX version in the SSE. I was just wondering, has anyone tried out? Because I intend to try it out.
Okay, yeah, I got your point. Maybe the larger gains are coming from AVX2 usage. So maybe we will try out a version using SSE2 when everything is settled down, and I'll update you.
Okay. Thanks.
Hi. So actually, looking at the current state of pull requests, it's actually failing because the AVX is not supported. So I think we really should have some kind of fallback version because when you build binaries for distributions, for example, it's not using AVX flags in the compiler to make it portable. So only when we have custom build, you would actually have the vectorized instructions. Second, it was a good comment about process locality. Maybe we need to think of some way to detect or have some information about the distance to the buffer that we're copying to or from. I think it's also useful in other types of CPUs. Not sure if how big is the impact if you're using this memcopy version if you're not crossing NUMA. So do you have this information?
Yeah. There are two parts in your question. One is what happens if the mem copy is between two processes. They are located in the same L3. Yeah. Okay. So currently UCX, I don't have any mechanism to identify at the lower layer to detect whether this transfer is between this core and that core. So that is not supported yet. And secondly, if I look at the sizes for some certain sizes, let's say 3/4 of L3 cache or more, even if two processes are in the same CCD, this non-temporal way of transfer is helping to reduce the latency. Okay, so before that version I just pushed 2 days back. So to answer your question, to make it work for the lower sizes, I need a mechanism in UCX to identify this transfer is between core number A and core number B. So I think we can work together for that.
The question is how useful would that be? If it's worth to add such mechanism. I mean, if the performance is also better on the same NUMA, then it's not useful enough.
Yeah, so performance will not be good in the same NUMA if we use this way of transfer for smaller sizes. It will benefit only if two processes are in different NUMA or different L3 for let's say sizes less than 256K or at that range.
Mm-hmm.
Yeah, so for smaller sizes, it will not benefit if they are in the same L3 domain.
Okay.
Any other questions?
Any other questions? Also online, maybe?
So one quick one. Just curiosity. What's the largest? No, it's okay. You can just repeat it if you want to. But what's the largest scale of number of GPUs that UCX was running on? Do you know?
So that's a good question. So I know that, as far as I know, the Microsoft cluster that they submitted, where they submitted HPL data this year in June, was using OpenMPI and UCX. And I think that one had like 18,000 GPUs. So quite significant, yeah. All right, any other questions? Okay. Thank you.
Thank you.
Okay, great. All right. Hello, everyone. Thanks for joining. My name is Hessam Mirsadeghi. I'm a software engineer at NVIDIA, and I'm going to talk about our effort for adding a UCX backend to Rallum. And let me start by giving a brief overview of what Rallum is. Rallum is an asynchronous low-level runtime that is designed for heterogeneous distributed memory machines. It is a kind of runtime that provides an abstract machine model of the system on top of which it runs. And it mainly abstracts this system in terms of a number of processors, including both CPUs and GPUs on that distributed system, as well as the corresponding memories. And today, Rallum is mainly used in the LLR software stack. LLR stands for Legate, Legion, Rallum. This is a software stack that provides a foundation to construct a composable software ecosystem that provides transparent scalability to the end users, scalability to both multiple GPUs and multiple nodes. As shown in the picture on the right side here, at the very top layer of this software stack, we have different Leagate libraries, such as cuNumeric, Leagate JAX, Leagate Pandas, and etc. cuNumeric, for instance, is a replacement for NumPy that has been implemented on top of this software stack. And the thing is, when you write your application using these Leagate libraries, you write the application once, and then you can run that on a single node, your own laptop, or on a system with or without NVIDIA GPUs, maybe Grace CPUs, and all the way to a DGX SuperPod, all the way to a GPU supercomputer. And the good thing is that on all these systems, this software stack, taking advantage of the Ralem runtime, automatically leverages all the available hardware to provide the best performance to the end user. And in addition to this software stack, that is LLR, Ralem can also be used directly as a runtime for your distributed machine. And that's in fact how the Omniverse team at NVIDIA uses Ralem for some of their use cases. And let me also give a quick explanation of how Ralem is different from a more traditional runtime, such as MPI, a well-known runtime such as MPI. There are a number of differences, but a key difference lies in the fact that Ralem is what we call an explicit representation runtime. And what we mean by that is that with Ralem, you model your parallel application, your computation, in terms of an operations graph. And in this graph, every node is either a task or it's a copy operation. And the edges in this graph capture the ordering and dependencies between these different operations. And Ralem provides a very lightweight, efficient event mechanism that the user can use to chain these nodes in the graph. This graph is generated dynamically at runtime and is submitted to Ralem. So Ralem has direct access to this graph. And because of that, it will take the responsibility for all the synchronization and the scheduling. Unlike something, for instance, with MPI, where this is something that the programmer needs to do himself. So with Ralem, not only this burden is removed from the programmer's shoulders, but this also enables the runtime to recognize more opportunities for overlapping these operations, and also do this in a portable way, so that when you move from one system to another system, you can get the same benefits without the programmer needing to go back and change the code to get better overlap opportunities on a different system. And being a runtime, like any other runtime, if you want to deliver good performance, the end users, it is essential to lower the runtime overhead themselves. And being a runtime designed for distributed memory machines, and those systems, you have the additional cost of communications that you have to make sure that you minimize them if you want to deliver a good performance. And this is where U6 comes into play. Communications in Ralem, more specifically, are funneled through what we call a network module in Ralem. Ralem is composed of different modules, and one of them is the network module. Network module is an abstract module that needs to be implemented by specific communication backends. And what this module mainly provides is an abstract active message API that is used for both data copies, transferring data from one node to another, and also for Ralem's internal control messages. There already existed two implementations for the network module in Ralem, one based on GasNet-EX, another one based on API. And as a result of our work, we have now added an implementation that uses UCX directly. But let me mention, why did we add a UCX backend, even though we already had two other backends? What were the motivations? There were a number of them. One is that using the UCX backend would allow us to take advantage of the latest hardware and software features when it comes to optimizing communication performance, such as RDMA, GPU direct, scalable transports in InfiniBand, such as DC, and in near future, DPU, and the list goes on. And in general, new NVIDIA networking innovations and technologies, when it comes to the software layer, exposing them to the software layer, they are exposing UCX. Another motivation was because it is essential to deliver the best point-to-point communication performance for both CPU and GPUs when it comes to the communication backend for RALM. And when it gets to that, U6 is the library to use. A lot of expertise and effort has been dedicated to make sure that U6 provides the best communication performance, point-to-point communication performance for both CPU and GPU buffers across different system types and networking technologies. And for NVIDIA specifically, having a U6 backend would enable us to have fewer external dependencies. And last but not least, using UCX will provide us with a good foundation to support some future requirements that RALM has, most notably elasticity and fault tolerance. And these are things that are difficult to achieve if you have dependency to MPI or GasNet-EX, for instance. Here I want to highlight some of the requirements that RALM has from the communication backend, from the network module, and how different U6 features satisfy those requirements. The first one, of course, is to implement an active message API. And this was nicely supported with UCX because we already have an active message API at the UCP layer. And the second one was with RALM, all the runtime operations must be non-blocking. And thankfully, UCX provides non-blocking versions of all communication operations at the UCP layer. Another requirement was that RALM wants the communication progress to be explicit. And more specifically, what I mean by that is that RALM doesn't want the communication backend, being UCX, for instance, in this case, to spawn any internal threads that are used to progress communications in the background. It wants communication to be progressed when RALM threads actually try to progress it. And this nicely matches with the progress model that we have in UCP, where you have to call UCP worker progress explicitly to progress communications. Another requirement was multi-threaded support, and it is already provided with UCX, so you can create the UCP worker with UCS thread mode multi and get multi-threaded support and multi-threaded safety. Pre-registration buffers was another requirement. With RALM, there's this initial phase where RALM passes these so-called network segments or communication buffers, basically, to the network module. And the expectation is that the network module should do any kind of optimization that it sees fit to provide a better communication performance later when those communication buffers are passed to the network module. And for instance, in case of InfiniBand, this goes back to pre-registration of the buffers. And this is, again, actually supported with UCX because at UCP level, we have a UCP mem map, which has been designed for this purpose. You pass the communication buffer to UCP mem map, and it is mapped to the different memory domains internally in UCX. And with InfiniBand, for instance, it translates to registering those buffers with the NICs. And then efficient zero copy transfer of these pre-registered buffers. That's the requirement. And this is, again, supported nicely with UCX because we have the registration cache and also a set of zero copy protocols in UCP. And also efficient one-sided data transfer. And this is, I want to say, mostly supported by UCP. I say mostly because there are some performance inefficiencies there, but we have UCP one-sided put and get operations that can be used for that. And also performant GPU to GPU communications is essential for RALM runtime. And that is supported with UCX thanks to the GPU awareness that we have in UCX and the fact that we use GPU direct RDMA when it is available, and also the topology awareness that is baked into UCX to take advantage of the GPU and NIC affinity to deliver the best performance. Fault tolerance is another requirement, and this is better supported with UCX because we have a more isolated error handling mechanism with UCX compared to something like, for instance, MPI or GasNet-EX. And elasticity, more of a future requirement, I would say, and that would enable us to add and remove additional nodes on demand based on the workload changes or in order to react to faults in the system, for instance. And for that, we want to be able to dynamically create and remove endpoints. And this can be nicely done with UCX. All you have to do is simply create a new UCP endpoint. And for that, you need either the remote worker address or the IP address of that remote node. And you can use also the client server API for creating the endpoints. With that said, let me show a performance result here. I'm showing performance for Ralem mem speed bandwidth test, and I'm showing the results with both UCX and the GasNet-EX backend. These results are across 2 nodes, and each node has 8 IB HDR 200 gigabit per second NICs, and there are also 8 A100 GPUs on each node. And I'm showing the results for both host-to-host and device-to-device, GPU-to-GPU communications. The orange bars show the result for UCX, and the blue ones show the results for GasNet-EX. And if you look at the 2 bars on the right side, you will see that with the UCX backend, we have been able to achieve 4 times higher GPU-to-GPU bandwidths compared to GasNet-EX. And that's thanks to the CUDA awareness and the topology awareness that is baked into UCX. Well, of course, not everything was rosy and perfect when we wanted to implement a UCX backend for Ralem. We did face some challenges and some feature gaps. And in the remainder of my talk, I want to discuss them a little bit. The first challenge that we faced was this mismatch that exists between multi-GPU usage model in Ralem and UCX. Ralem is mainly designed for a multi-GPU per process usage model, where on each node you have a single process, say a single MPI rank that manages all the GPUs on that node. Whereas UCX has been mainly designed for a single GPU per process usage model. So for each GPU, you need to have a separate process. And as a workaround for this mismatch, what we had to do is to create additional UCP contexts, and more specifically, create a separate UCP context for each GPU. That would allow us to set the correct GPU context before calling UCP init for each of these UCP contexts to take advantage of the topology awareness that we want. And we also have to, in addition to that, push and pop the correct GPU context before and after UCP communication operations. A main caveat with this design, with this workaround, is that it leads to extra endpoints. Now we have to create an endpoint from each UCP context on each node to every other UCP context on other nodes. And these extra endpoints translate to additional overhead when it comes to communication progress. And basically translates to using more CPU cycles to progress these communications, because now we have more endpoints that we need to pull. The desired solution that we want to have instead is to have this native multi-GPU per process support in UCX. And that will allow us to move from this picture on the left side to the picture on the right side, where we will only create a single UCP context on each node, and then we only create one endpoint between those 2 nodes. And that means we will move from a number of endpoints that is currently in the order of n times GS squared, where n is the total number of nodes and g is the number of GPUs per node with this workaround that we have. We will move from that to an O of n number of endpoints. So a factor of GS squared reduction in the number of endpoints. Another challenge that we faced was related to multi-threaded support and multi-threaded usage, and more specifically, the fact that we have this coarse-grained UCP worker lock. To explain that, let me say that for the Ralem runtime and the UCX backend in Ralem, we use UCP AM send NVX to submit active message communication requests. And this function is called by multiple Ralem threads. And on the other hand, we use UCP worker progress to, of course, progress the communications. And the UCP worker progress is called by Ralem background worker threads. There's a pool of threads that Ralem uses for what we call background work items, and progressing the communications is also a work item. And the UCP worker progress is called by the threads in that thread pool, but it is called in a serialized way, meaning that only one thread from that pool at a time calls UCP worker progress on the given worker. And in addition to that, we also call UCP AM data release to give back to UCX the internal persistent buffers that are used for active message eager reception. And these are this function is again called by multiple random threads. These could be the background worker threads or could be other random application threads. And all of these functions directly or indirectly access the UCP worker. And to provide thread safety and synchronize these threads, of course, we create the UCP worker in the multiple threaded mode, and it is the worker lock that provides that safety. But the problem is that we face two main issues with this locking way and the synchronization between all these functions is that one, we get contention between AM send submission when the application thread wants to submit a communication operation and the progress for incoming messages when we want to receive the messages and we're trying to progress those. We will have contention between these two and also releasing the internal buffers, which is unwanted because these could be done by different threads. And this becomes specifically bad performance-wise if the operating system happens to context switch one of these threads while it holds the UCP worker lock. Then everything is paused with respect to the network module, U6 backend. Nobody can make any progress until that thread is, again, scheduled back, make some progress, release the UCP worker lock so that someone else can acquire that. So we noticed that when there was some oversubscription, this significantly degraded the performance. Now, as a workaround for this, what we did was we used two separate UCP workers. One UCP send worker and another one, we call it UCP receive worker. The UCP send worker will be similar to the UCP worker we had before. It is created in a multiple thread mode. And it is the worker that we use to submit active message communication requests, namely UCP AM send NBX. And we also call UCP worker progress, of course, on that UCP worker to progress those send operations. But on the other hand, on the UCP receive worker, we don't submit any communication operations. There's no UCP AM send NBX that is submitted on that worker, and that worker is only used to receive messages. And on that worker, we call UCP worker progress, of course, to progress it, and also UCP AM data release. And these two now are done sequentially on that UCP receive worker, meaning that every time a random background worker thread wants to do some progress work, it first calls UCP AM data release to release some internal buffers, and then it moves on to calling UCP worker progress on that receive worker. And now this means that the application threads or other random threads do not call UCP AM data release directly. What they instead do is that when it comes to returning those buffers, UCP internal buffers, they just add the corresponding descriptor to a queue, whose elements are later on consumed by those background worker threads when we want to call UCP AM data release. There are a number of benefits with this workaround. One is that we no longer will have a contention between AM send submission and the progress for incoming and receiving messages. And AM send NBX will not contend also anymore with the threads that want to return UCP internal buffers. Another benefit is that with this model, and because the progress work and that UCP AM data release is now only called by random background worker threads that are already serialized, we don't need to create the UCP receive worker in a multi-threaded mode. We can just use a serialized mode, which means then there's actually really not any lock that needs to be acquired and released when we want to call UCP worker progress or AM data release on that worker. And of course, we have this additional lock on that queue, but the scope of that lock is now much smaller, and the contention is only between the threads that want to return the internal buffers and the background worker threads that want to progress the receive worker. And with this design, specifically, when it comes to a UCP AM data release, the thread that wants to call that views a try lock on that queue. So that if we could acquire the lock, we do it and release some internal buffers. If not, we just move on. We don't wait. I also want to mention some of the feature gaps that we faced. I think the most notably and probably the most important one was being able, having some means in UCP to provide Realm with the information that it requires to build its so-called DMA graph. Let me first explain what the DMA graph is. Ralem internally builds a graph, a DMA graph, where the nodes represent memory regions, and the edges between these nodes represent the communication channel between those memory regions. And when it comes to the network module and the UCX backend, we are mostly interested in a subgraph in this graph that corresponds to memory regions across different nodes. And it is for that graph that Ralem needs some information from the network module, in this case, UCX. And more specifically, it requires information to be able to, it requires information when it comes to adding the edges in this graph. Ralem wants to know if it should add an edge between M1 and M2, M1 and M4 in this graph, for instance. We can ask for a number of different features to satisfy this requirement, and I want to discuss two of them. One is what I call a minimal UCP feature, and that would allow Ralem to add an edge between these nodes based on whether a zero copy transfer is possible between the corresponding memory regions. So at the very least, what Ralem wants to know is if zero copy transfer is possible between these two memory nodes, then Ralem will add an edge in the graph between those two nodes. And if not, it will not add that edge. And in order to provide that, one way that we could do that at the UCP level is to provide a way for the user, Ralem in this case, to disable copy-based protocols, or more specifically, protocols that do some kind of staging. And then after that, query UCP whether it can do data transfer from a given communication buffer. And if it can, then it means that it will be zero copy. So Ralem will go ahead and add an edge. If not, then it means it is not possible to do zero copy. No edge will be added. But this is not the ideal feature that Ralem wants. And the ideal feature would be something where UCP will provide some kind of API for the user to query about details of the protocols that UCP will use for communications. More specifically, an API that Ralem can use and ask UCP, hey, what are all the possible protocols that you can use to transfer data from this given communication buffer? And also tell me what is the latency and bandwidth that is associated with each of these protocols. Today, UCP actually has this information with the new protocols, with protocols v2, we have this information, but we don't really expose it to the user. And internally, UCP uses this information to select what it thinks is the best protocol to use for communication from a given buffer. So one way could be to provide an API to expose this information, let the user know about all the possible communication protocols, and with their corresponding latency and bandwidths, and then also provide a way for the user to specifically choose one of these protocols and force a specific protocol per operation. For instance, when I want to issue a UCP AM send NBX, I would somehow tell the API that I want to use this specific protocol that you told me about before that you can use. I know that the latency and bandwidth might not be optimal the way that UCX sees, but there are cases that Ralem actually wants to use something that looks to be suboptimal from UCX's point of view. And the reason for that is that Ralem has a global view of communications, of resources that are being used over that system compared to UCX. UCX only can make decisions that will be locally optimal with respect to just one communication request. And let me say that these edges in this DMA graph are labeled edges, and they are actually labeled with the latency, bandwidth, overhead, and also even the dimensionality of the communication channel. And today we cannot provide any of that information. Ralem just assumes some numbers. So if we can provide this information, those edge labels will be more realistic. There are a number of other feature gaps that I will mention them quickly. One other feature gap we faced is the ability to query UCP. What would be the maximum message size that it can transfer without doing any fragmentations internally? And Ralam wants to know that because Ralam already does some fragmentation of the buffers for some other reasons that it has. And because of that, it wants to avoid any extra fragmentation in the network module because that would really be unnecessary. And this way, Ralam wants the network module to avoid any memory allocation, copying, and reassembling of the messages on the receiving side, for instance. Today, we don't have a way to actually ask UCP about this. And we're currently using some kind of a hackish workaround where we set, for instance, in case of IB, we set explicitly the IB segment size, and then we report that to Ralam as the maximum single fragment message size that U6 can transfer. Prioritized communications is another feature that we would like to have, and that would basically allow us to assign different priorities to different active messages. At the very least, for instance, we can say this message has higher priority than the other message. And the most important use case of that in Ralam is being able to prioritize certain small messages, certain small control messages whose latency is very important, is very critical for the overall performance of the runtime, compared to, for instance, large application data transfers. Today, what can happen is that these small control messages are stuck behind these large data transfers over a given, for instance, queue pair. And as a workaround today, what we're doing is that we create separate endpoints over a completely separate worker to sort of, at least to some extent, we can separate these messages from each other so that the small ones don't get stuck behind the large ones. And last but not least, it would be good to be able to enforce ordering between active messages and RDMA operations. That is extending the ordering semantics that we have today with UCP so that they cover active messages as well. That will specifically allow us to use something like UCP put to remotely write the payload of an active message on the remote destination node, followed by like a header only active message that is sent to the destination to trigger the receive active message handler. Today, we can't do this in this way, and what we have to do is we should do a UCP put and then do a complete flush on that endpoint and wait for the completion of that flush and then issue the active message. Whereas what we actually need is simpler than that. We want to be able to say something like UCP put, then a fence, and then issue the active message and wait for all of those to complete without doing a flush and waiting for the completion of flush first and then issuing the active message. And that's all I had. Thank you very much for your attention. Let me know if you have any questions.
Is the room mic working now? People online, can you just hear us?
I can hear.
Like, is the interference gone? Because that's why we had to get this in the first place.
Sounds good now.
Yep. I have a couple of questions. Can you hear me?
Yes.
Yes, thanks. It was quite interesting presentation regarding the single message fragment limitation that you would like to know the maximum supported single fragment message size. There is already some kind of workaround you can use. Instead of setting IB segment size, you can query for maximum active message header size, and it's guaranteed that it will not exceed a single fragment. The drawback of this approach is that it may not be the maximal possible fragment in the system. For instance, if you have UD transport with just fragment size up to 4K, then it will be 4K, a little bit smaller than 4K. But otherwise, if you're using just DC, for instance, it will be like IB fragment size. So it is implicitly guaranteed that it will not be larger than a single fragment size.
Mhm.
It's not a clean solution, but something you may consider.
So I actually today do query the maximum header size, and I remember that it is at least on the systems that I tested, it is lower than that maximum segment size. For instance, I see that the maximum header size in my tests was something around 3K, 3.5K, for instance, and the IB, for instance, segment size is 8K in case of RC, right?
Yes.
So as you mentioned, it's guaranteed not to be more than that, but it could be considerably smaller as well, right?
Yes. Yes, not sure whether it fits your needs, but at least something you may consider. And another question about the ability to specify what protocol to use. When you mean that, when you say that you want to avoid copy during the message transfer, do you mean just sender side or both sides?
I would say both sides, especially when it comes to copying between host and GPU.
Okay. I mean, for active messages, it may not be that difficult to implement because we already have specific flags which forces active message, which forces particular protocol to be used for active message. Maybe if you can clearly define the behavior you would like to get from active message API, maybe we can add other flags like.
Well, those flags are used to enforce the communication protocol to some extent when you're submitting an active message. But that is part of what we need to build that DMA graph. In fact, we don't really need that when we are building the DMA graph. We need that when you're submitting operations. But for building the DMA graph, that flag doesn't give us any kind of information that we want.
No. I mean, when you submit operation, you may define some new flag. For instance, no takes copy or no RX copy or no copy. And that flag would mean that UCX is not allowed to select a protocol which implies copying data is on sender or on receiver.
Right. Yeah, that would be actually helpful. Yes.
Yeah, if you,
but that alone will not help, right? So what we also need is to be able to ask UCP before that, like asking it once at some kind of initialization phase. If I were to disable the copy protocols, can you still transfer data between, let's say, this pair of communication buffers? Because if UCP will only use, for instance, a copy-based operation between a given pair of communication buffers, we want to know that ahead of time, right?
Okay. Okay, so then we'll have to also add some query attribute for a worker probably.
Or if we can provide the ideal solution, I mean, kind of ideal, which is exposing different communication protocols that the UCP can use. Because the thing is, I look at it this way, if we were to implement this backend on top of UCT instead of UCP, would that give Realm what it wants? And the answer seems to be yes. It would provide Realm with everything it needed in terms of building that DMA graph and doing that enforcement, which was something that we considered when we wanted to implement this backend, whether we should use UCT or UCP. But we decided to use UCP because then we had to re-implement and reinvent a lot of goodness in UCP that we would also need in that UCT backend.
I see what you mean, but even with UCT, you would need to use two different parts of API. So how to say, you would need to rely on capabilities flags from interfaces, and also you would be able to select a particular protocol when sending data. So here in UCP, even if we expose all the protocols through some query mechanism, you still have to have some flag or an ability to
exactly.
specify
Yeah.
what protocol to use when you're actually posting the data.
That's right. That's correct. And actually, that is why, let me share this again here. That is why I have, yeah, I say 1 and 2. That means we need both of these, right? That query about those protocol details and also enforce a specific protocol. So you're right. I mean, we need both of those.
You actually want to make a decision of whether to pack the data into a GPU buffer or a CPU buffer based on some information from your CPU, right? That's why you need to query.
Can you say that again, Yossi? I had a little difficulty hearing you.
Maybe I'll take the microphone. Can you hear me?
Yes, much better.
Okay. So you want to decide whether to pack the data into GPU buffer or a host memory buffer based on information from UCP, right? Based on.
And that's one of the use cases. That's not all of it.
What else?
For instance, one other reason we want to be able to enforce specific protocols is, in some cases, RALM, if UCP is going, for instance, to use CUDA copy in a staging protocol, RALM wants to have to have the ability to tell UCX, don't do that. Either use some other protocol or let me know if you're using CUDA copy, then I don't want to pass that buffer to UCP at all.
So
because RALM has a more global view, it is using the copy engine for some other things at that point in time. And if UCP ends up using the copy engine, it will interfere with other things that RALM is doing and are probably more important at that point for RALM. So if UCP tells RALM, yes, I can send this data from this GPU buffer, and it's not going to use CUDA copy, or then RALM is, okay, please go ahead and do that. But if UCP says, I'm going to do it, but I'm going to use CUDA copy, then RALM might say, okay, forget about it. I don't want to do that communication now. I'll do something else about it. At some other point, I will do the staging myself when the more important copy that I'm doing right now is finished. It's all about prioritizing different operations in the runtime that RALM is aware of them versus UCX.
But first, you would like to know which kind of resources or hardware resources a specific send operation is going to use.
Mm-hmm.
For example, copy engines on GPU, and also you want to decide whether to send this at all, or maybe also to send it with some restrictions without using those.
True. I mean, ideally, if we can know all the protocols, the latency and bandwidths, and also know a little bit about what those protocols include. For instance, a CUDA copy, or is the GDR copy, or at least is it copy based or not? Then RALM will have more information to make the decisions at once.
But it's important if it's CUDA copy or it's some other kind of copy, because you really care about the resources that CUDA copy is using.
It matters. Like if UCP tells RALM I can do this copy with GDR copy, then RALM might say yes, please go ahead and do that. But if it says it's going to be CUDA copy, RALM might say no, don't do that. So yes, the copy, the way that you do the copy matters as well.
Mm-hmm.
But I think it's like it's not a 0 or 100 feature request in a way that if that part, for instance, cannot be provided, it's not a deal breaker, I would say. I mean, ideally we want that, but as I mentioned, a very much more simple thing that UCP could provide is far from ideal, but much better than not having anything, which is the case today, is to at least enable RALM to disable copy-based protocols and then query UCP if communications are still possible.
So it seems like the gap here is that in some frameworks that use UCX, there is some global knowledge.
Exactly.
Does not have that knowledge. Maybe another use case is collective library, where you have some kind of global knowledge. And you want to pass that down to the point-to-point library somehow, but also in a generic way.
Right. And again, as I mentioned, I think to myself, is if this was UCT, then Rallam could do that, right? Because it would not be UCP to making the decision about the protocol. Rallam would already know about the latency and bandwidth of the different transports. And it knows what kind of copy engine every transport uses, and would have everything it wanted.
Right.
The information that it needs and also the control that it needs. But we don't really want to remove many of the benefits of UCP because of that, and use UCT directly, right? So if we have this flexibility of choosing the protocols and knowing about the protocols, we will be happier, much happier to use UCP than UCT.
Yeah, but it shouldn't be too detailed because it has to be future compatible.
Mm-hmm.
But you'd also, yeah, trying to think what would be useful also for collective libraries because, for example, if you know that we're going to use certain NIC from several processes at once, or only one process is going to use it. It's kind of similar to the copy engine.
Well, in a sense, yes. And well, what today, and the thing is, Rallam is more interested to have control when it comes to the resources or transports that Rallam itself also uses for other things, like for instance, the CUDA copy engine, right? Today, when it comes to NICs, Rallam doesn't care about that because Rallam doesn't use the NIC for any other thing today, right? But if in future, let's say we have a NIC that Rallam is also interested to use it for some other purposes, for its own purposes, then in that case, yes, we might want to know something like if UCP is going to use that NIC, then no, I don't want to do the communication now because I'm using the NIC for something else. But today, that's not the case. When it comes to the NICs, because Rallam doesn't use them at all, there is no conflict between UCP and Rallam in that sense. But when it comes to copy engine, for the GPU, there is such conflict.
Mm-hmm. Let me quickly clarify. You mentioned you want to know bandwidth latency of protocols, which I think would be very hard to achieve, given that UCP can use completely different transports depending on the peer locality. Do you think it would be enough if we can provide some ability to specify whether you want to have any kind of copy on sender or receiver, like no send copy or no receive copy, and you would be able to query whether UCX is able to do that for a certain type of memory. I mean, avoiding any type of copying.
That will help. That would be, I think, that minimal feature that I listed. But I think when I think about that, I think we need to be able to distinguish between certain copies, at least at the receiver side, because if I send an active message and it's eager, there will be some copy at the destination side. So we want to exclude that, right? If it is like a host-to-host active message and it's sent eagerly, that is fine, right? I mean, receiving it eagerly in UCP internal buffers and then passing it to Rallam is fine. But if it means receiving it on host and then there has to be some kind of CUDA copy to GPU, then that is not fine.
It shouldn't be a problem because you have to specify a specific flag when posting active message. Mm-hmm. And for instance, if you mean that you will be able to post eager flag together with no copy, it will be conflicting flags, and we can describe that in API that these two flags are not possible to use together.
Yeah, but how can I say I don't want any copy, but I don't want that to translate to rendezvous always for UCP active messages, at least if it is host to host, right?
So it's not possible because eager always implies copying data on the receiver unless you're just using a network buffer pointers. But what we can do is that we can limit eager by maximal fragment size. I mean, currently we may send eager as multi-fragment message, But if you specify something like no copy, we will be using Edgar for small messages where it is still possible to have no copies on both sides. And then we will switch to random.
Yeah, if that no copy flag doesn't necessarily always translate to disabling eager, then that's okay. That's what I want to have, at least when it comes to host to host. I don't want that no copy to translate to disable eager completely, because there is always some, I mean, not always, but if it's not persistent buffer, there will be necessarily a copy.
By the way, if we pass CUDA streams to the operation, and that stream is going to be used for CUDA copy, would this help somehow?
I actually don't know, because it would still use the copy engine, right? And still Ralom will not have control, and will not really know if the copy engine will be used or not.
Just I think what you may be hinting at is that if a stream is passed to a UCP operation, then you'd be able to query if there would be a CUDA copy operation or copy engine operation down the road. Is that what you're hinting at?
Maybe if we have some special value of stream, like invalid stream, which would mean to disable CUDA copy.
But also another thing I wanted to say was we're assuming that CUDA copy will be the only one used for copies, but there's also GDR copy being used, so we would need to distinguish those.
Seems like Legion mostly cares about CUDA copy because of using engines on the GPU, not necessarily because we're copying something, but because we're using some hardware resource.
Yes, but also there's the aspect of PCI contention, right? Like if Legion knows that there's PCI traffic because of some of its own activities, I think it cares either if CUDA copy or GDR copy is currently also going to use it at the same point.
So we want some kind of query operation that describes the flow of the protocol, including all copies and engines, or some description of what's going to be used during the operation.
I think knowing about, I would prioritize it this way. Highest priority is knowing whether it involves copy or not, regardless of what engine, or even if it is CUDA at all or not, right? Even copy and staging for host to host on the sender side, for instance, for whatever reason, for instance, using bcopy, that is something that we want to know, right? So priority one would be able to know whether this protocol will involve stage copy, bcopy or not. And then on top of that, if we know that, yes, it involves copy and it will use the copy engine for the CUDA copy, for instance, that would be like an additional benefit. But the first one is more important than the second one, I would say.
Okay. We want to also discuss fragmentation. So I think the issue here is that when we receive multi-fragment active message, currently we have to assemble the fragment into one buffer and do malloc and copy. That's a big overhead. What if we have some plan to implement a multi-fragment active message, which means that you specify a callback that is able to process each fragment separately, not necessarily having them all in a single buffer. That should not have a significant overhead compared to, let's say, a single fragment. Would that be good enough? Or would
but it will still be fragmentation, right? What mainly Ralom wants is to exactly know what message size will not involve any fragmentation. Again, because fragmentation is already being done by Ralom for some other purposes. And Realm will ask UCP about that, and then later on will only pass UCP the payload size that UCP has told Realm can be sent in a single fragment. So I would think these two features are orthogonal. I mean, it's good to have the one that you mentioned so that we minimize the overheads of fragmentation. But it still doesn't answer that query for Realm.
It's not that difficult to implement on EP level if it will be sufficient for you. I mean, we can extend EP query to return a maximal fragment size because it can be different per endpoint, so it has to be an attribute of endpoint.
Exactly. Yeah.
So I think it's a relatively small change if it's just returning a maximal allowed fragment for every endpoint.
Is it for every endpoint or each specific protocol? Because could it be that we use a different transport for a different message size or a message buffer, for instance, based on the location and type?
Yeah, it's possible. The question is, we can get the absolute minimum of all of the possibilities. Like, what would be the maximal size that is guaranteed to be without any fragmentation?
Mm-hmm.
It could be rather small, like 8 kilobytes, for example.
Which is the case today as well, right? I mean,
the question is, if you want to distinguish between, let's say, eager and rendezvous fragments.
This would be for eager.
Yeah.
This would be for eager because the way that Realm asks UCP, we can distinguish between those two. I can see ways that we can distinguish. So if we know that the maximum fragment size for eager, I think that will answer our question. So and if we can also say what is the maximum for rendezvous as well, that would help too.
Is it important to distinguish between them?
It is because the way Realm asks that question is, if I give you this communication buffer, this source buffer, what will be the maximum payload size that you can send in a single fragment? And another API is, if I give you this source buffer and this is also the destination address that you have already provided, for instance, the R key for me, what would be the single fragment size that you can transfer? And those two will be different, right? Because if I have GPU direct RDMA and you're passing me a source GPU address and a destination GPU address, and I know that, for instance, I'm going to use get Z copy, then the maximum message size in a single fragment can be quite large, right? It is not limited to that segment size, for instance, anymore. So for those cases, we want to actually return the maximum size that we can transfer in get Z copy, for instance.
And how's Realm doing the fragmentation?
What do you mean, how?
I mean, is it possible to bypass somehow the fragmentation on Realm level and pass the buffer to UCX as is?
I actually don't know, but I speculate the answer is no, because as I mentioned, it is doing it for other reasons. It's not just because of the fragment size for the network module.
Okay, another option is, what if we had like relatively large fragments on the Realm level, and then the additional fragmentation that we have on UCX, even if it's not the same size, should not make a big difference on performance.
I think one main thing that Realm wants to avoid when it comes to fragmentation as the network module is, again, prioritizing that operation. When Realm does the fragmentation itself, it has a better idea of when it is least hurtful in terms of performance to do the fragmentation.
What does it mean?
Again, in terms of prioritizing this fragmentation, for instance, versus spinning cycles for the application tasks themselves.
I mean, if Realm decided to do fragmentation, it can make a better decision as to how to spend the CPU overhead.
When to do it, I think that's one of the things that Realm knows better than UCX. But again, I'm not 100% sure about that, but I can check it.
Okay. And regarding the order between put and active message, so a signaled put, is it going to solve the issue here, or we still need the ordering?
I think the signal put will solve it. Can we use that to trigger the active message handler?
So it's like a put with active message, not just a signal that flag.
Yeah, that works. So what we want is the payload to have been already written on the remote buffer before that active message handler being invoked.
I have a question. I wonder if IB has that, no? InfiniBand?
It has, but it's kind of limited because the signal size is 32-bit. When we implement such API in UCX, we can decide what is the better way to implement, whether to use IB or something else.
But I mean, I don't know, maybe I recall wrongly, but I think there is an ordering between a send and a write that you get. So the send is going, so your write is going to be completed whenever your send completes. Is that correct?
So there is ordering. The reason this UCX is more complicated is because there are multiple devices, multiple transports. In some cases, we need to synchronize between them. I think that your intention may be that instead of using full-fledged flash operation, we need to extend the semantics of UCX fence to insert ordering between active message and put. If there are some implications regarding multiple devices and multiple transports, we have to handle it internally. But if we have API of put plus active message or something like that, it will have more chance to optimize things compared to a global fence operation that cannot assume anything. By the way, what if we use the active message with rendezvous? In this case, if you use a rendezvous active message, you can send the active message and then you would do RDMA read instead of puts.
That's actually what I'm using today. So for sorry, what?
Why would the RDMA write with signal be better than that?
Because we will have less round trip latency, right? Because and the fact that with rendezvous, I have to wait for the receiver side as well. Today I do enforce rendezvous. So if you give me the remote address, I send the active message enforcing rendezvous, and then that way I can trigger the active message handler only after receiving the payload has been finished. But one issue, for instance, with that is if I'm sending very small messages, for instance, I'm enforcing rendezvous.
So, and you do know the remote address up front, right?
I do know it, yes. Yep.
Is Realm taking care of that?
It's taking care of that, yes. So it has already passed those communication buffers that it will use in these cases already to UCX, and then they have been passed to UCP memmap. Yeah. So a put with notification will have less round trip latency.
Okay. And regarding the prioritized communication, so we plan to implement such feature in a next UCX release. The idea is passing priority to each operation. And when we do that, it means that there is no longer ordering guarantee between active messages.
Right.
That.
Right. And yeah, go ahead, please.
we had some thoughts about what the API should look like, whether it's going to be like high priority and low priority, or some small set of numbers to define priority. Do you have any thoughts on that? What would be preferred?
I would say if we can like initially ask UCP for a certain number of priority levels that we want UCP to support for us, right? Because one main thing that we want is to be able to separate these messages from each other. Because the priorities at the end of the day, when they translate to IB service levels and what virtual lanes, for instance, to use, those are the things that the application does not have any control over it. Realm doesn't have any control over it. So we might set certain service levels and priorities, and the NICs and the network switches decide not to respect it at all. So I don't think that is something that we can completely solve. But at the very least, what we can get is separate queue pairs. That I can put those smaller messages on a separate queue pair. And also, if I could at least have some impact on the arbitration logic on the NIC and say, at least for my own applications, for the queue pairs of my own application, if you can, please service this one more often. I know that today you can do it by setting quality of service configurations for the subnet manager, but that is like not something that that application can change and affects all the users of the NIC. But even if we can't do that per application, at least if I can have separate queue pairs, based on the benchmarks that I did, it still helps a lot to decrease the latency of those small messages. And the way I see it, then it would be ahead of time, we ask UCP, hey, I want support for, let's say, 4 levels of priorities, so that UCP knows that it should create 4 queue pairs, for instance, and not more. Or if I only ask for 2 levels of high-low priorities, 2 queue pairs will be enough for me. And that way, I don't have to create another worker and extra endpoints that, again, I have to pull. Hopefully, the overhead will be less.
Okay. Let's give the presenter a quick round of applause.
Thank you.
We're gonna Danino from NVIDIA. You're muted.
Oh, I'm muted. Okay.
There we go.
Sorry. And so, let's see. Tell me, oh, it's sharing the wrong screen. Fix this. Okay. Okay. So I'm going to talk about using in-chip memory for RDMA operations, which is also called MEMIC. My name is Roie. I'm from the U6 team, Leonid's team to be specifically. You know what U6 is. Okay, so what is InfiniBand MEMIC? It's a memory chip located on the InfiniBand devices such as ConnectX and Bluefield devices. And it can be accessed through RDMA operations from the CPU, or of course, it can be accessed from within the NIC, because the NIC can do some calculation by itself. And it can be, of course, accessible through the network or the PCI. Okay, so why would we even want to use such a memory? Let's say accessing a host memory through Accessing host memory in RDMA operations requires a round trip over the bus. In atomic operations, it can get to 300, 350 nanoseconds. And if we will allocate the memory on the network interface, we will be able to avoid that round trip because it can recognize when an address is belongs to the NIC itself, and it will not go over the bus for that to access that memory. Okay, so a little demonstration. Let's say we're using host memory, and this is the PCI motherboard of a DGX, for example. So those will be the CPUs, and those will be the host memory. And these are the NIC controllers. We will just call them NICs. We will. So when we want to do an atomic fetch and add, which is a feature of the InfiniBand device, an RDMA request goes from the CPU to the NIC. The NIC needs to read the value from the host memory. That memory needs to be written back to the NIC. And then he calculates the addition. And then he needs to write back to the host memory the result. So this is how it's happening. It's happening right now with host memory. And with NIC memory, if we're allocating a NIC memory in first place and using it for atomic operations, the CPU sends the same RDMA request, and the NIC calculates the fetch and add, but it doesn't need to access to send messages over the bus, and just can calculate the add and write it back to its own memory. Okay, this is how it will look on operation over the network. If I want to write to some remote machine mimic. Okay, pretty straightforward. So this was already implemented in UCX. And if you want to use it over UCX, you need to use the new memory type called the UCS memory type RDMA. And in some way, this resembles allocating a GPU memory. Again, because it's a remote, a separate device memory, which can also calculate at least some of the operation. In a way, it's a different address space that we want to access, and here is an example of how to use it using it with UCX. So, of course, you need to set the field mask to tell UCP memap that we are setting the memory type field. We're setting it to the new memory type RDMA. And the memh will be the memory handle that which will point to the RDMA memory. You won't be able to access the RDMA memory directly, but you will be given an address that's mapped to the memory, which is not the actual address of the mimic. Okay, just like any other memory type in UCX, if you are familiar with allocating different memory types. Okay, so we also added a support in SHMEM, which uses the UCX API I showed earlier. And SHMEM malloc with hints is the new, it's an API that, as far as I know, supports only this flag, SHMEM hint device make memory. It was created for that purpose. And the buffer here that you're seeing in the code is you can't access it directly like a regular pointer. It's a pointer that mapped to the memic memory. And here's an example of doing some kind of atomic operation, like setting the atomic variable to 0. And let's see, if memic is not available, so host memory is allocated instead. Okay, so you will not get an error if you try to use memic and your device doesn't have support for it. Okay, so how it works in UCX is actually we are allocating the IB device memory through this verb, IBV alloc DM. And then we are reserving an address range matching the size of the allocation. And we're setting that memory mapping to be private. So this is the pointer returning to the user. So we wouldn't want the user to be able to access the memic directly or to think he accessing the memic directly. And then we need to register the RDMA memory using the regdmmr. You can notice that the address we're registering here for the RDMA is 0 because device memory on in InfiniBand devices are 0 based. That's why the flag here is mandatory. You can't reg the MMR without this flag, without the IPv access 0 based. So if you notice, we have some kind of problem because we want to give some kind of representation to the user that it's the address, and on the other hand, the actual address that's being registered for RDMA operation, it's 0. Okay, so sorry. So this is the problem. And the solution is to do some kind of mapping, which is a feature of the device. It's called the KSM. And we can use that KSM pointer mapping mechanism to map the address that we allocate, that we reserved with using mmap, sorry. We can use that address that we reserved using mmap to 0, which is the actual address the NIC referring to as the memic memory. So this is also allows us to use indirect memory mapping, not only for memic. That mechanism is useful for other scenarios, or when we want to, for example, using a remote key to some RDMA address. Okay, so we use the 2 benchmarks for atomic operations to measure the performance of memic over host memory. So we used, of course, we used the UCX perf test for the point-to-point kind of test with the single sender and single receiver in one direction. I think you can do bidirectional communication in PerfTest 2. And we use the two different benchmarks. One is the UCP fetch and add, which does the addition and returns the old value to the user. And we have UCP add, which just posting the add request to the NIC. Okay, so this is how the command line looks like. So this is the UCP fetch and add is the kind of test in UCX perf test. I guess most of you familiar with how UCX perf test works. This parameter is the affinity of the CPU. We're using CPU 0, and this is the most important parameter, the memory types that you can set for the sender and the receiver. The host is the sender memory type, and the RDMA is the receiver, it's the target. We used size. In atomic operations, the UCX perf test supports either 4 bytes or 8 byte operations. So I just went with the 8 bytes. It doesn't really matter at this point. And the last parameter, the O, is it stands for how much outstanding send are there. It's you can I named it here window size, and of course the other host that we're sending to. Okay, so these are the results. So here you can see when the window size is 1, we still see a major improvement. The latency was reduced by 14%, and the message rate was improved by 16%. In atomic add, we can see that the improvement is even larger here. But this side of the table is less interesting, in my opinion, because the sends are blocking each other. So when we're using a window size of 16, you can see that the message rate is like almost twice and a half better. And 70% of the latency is gone. So if we look particularly at the numbers, it's like almost like 3-4 times better latency. And when we are looking at atomic edge, we can see that latency is cut in half. We can explain that the difference in the improvements between fetch and add, that add doesn't have the extra round trips on the bus in the first place, because it doesn't need to fetch the user the old value, and it's less round trips over the bus. Okay. I used in this measurement, I used 2 nodes, of course, because it's point-to-point. Intel Radeon with each with 15 cores, and 2 connecting 6 devices. And this feature was released in V116. Okay, so the next benchmark was in SHMEM. And this is a benchmark we are calling contended atomics benchmarks. The idea here that we are allocating a single buffer. The user is allocating a single buffer that all the rest of the processes are using and adding 1 to. Okay, you have the code here. This is the benchmark itself, and this is some kind of pseudocode. The root process allocates an atomic variable. It can choose whether he is allocating on the heap or in the global memory or on memic. The value is being set to 0. We're doing a barrier, and then each process adds according to the number of iterations, which is an input to this benchmark. And then, of course, another barrier, and we collect all the results. And this is the distributed test, of course. We tested that with 15 nodes. And here in the table, you can, in the graph, you can see that we have like a major increase in performance until 15 nodes, because each node has its own NIC, so it looks almost exponential. And from that point, no nodes were added, so improvement is still there, but not as big as before when we added more nodes, with each process. Sorry, and it looks quite significant. On the right side, we're seeing the message rate per process. Here too, you can see a major difference from the point of the 15 nodes, or 15 NICs. And then when moving to 30 processes, there's a major drop in the efficiency of each process, but still much better than using heap memory. So here I use the same hardware from the same cluster from the previous benchmark. Each has 2 Intel CPUs and 2 connected 6 devices. And by the way, this feature was implemented for both V5 and V4 versions of OpenMPI. Although I think sorry, I want to go back to the usage. Okay, so I'm pretty sure that in V4, the API of alloc with hints is experimental, so you need to include the shmemix header. So also the signature of the function is a bit different. I think it's shmemix malloc with hint. But other than that, I had some conclusions. The main conclusion is that using memic for atomics improve the performance significantly. And if anyone has any question, I will be glad to try to provide an answer. No questions.
Is this useful for any other application use cases besides OpenSHMEM? Have you found any other use cases outside of OpenSHMEM?
I did not try other use cases other than OpenSHMEM. No.
Maybe injection. Can you inject? Can you inject? When you inject, can you use that?
Inject what?
When you want to avoid, you do an eager, and the payload is very small, so you can just directly copy there.
It's already done.
It's already done. Okay.
I'm just trying to, to see, okay, OpenSHMEM with Atomic, it's like one of the rare programming models that has Atomic. Clearly, it's like Really good.
NPI has one.
Really good. The NPI has one, but nobody using it. Because it was historically so bad, right? Maybe we'll start using it now. I'm just wondering if there is other programming models and maybe some use case in RAL for synchronization. Maybe you guys have to socialize, these benefits more with other teams. So they think very
Heard of such examples?
Hmm?
Have you heard of other users of atomic operation?
Explicitly atomics not, but I think we should think about in larger context, not the SHMEM, but what operations people trying to achieve. Think about like signal put, right, or counting put, which is another way to signal, right?
So I have a question. So for how large is this on-chip memory that we're talking about? I was
Get-
trying to the spec, but couldn't find anything.
I can't hear anything. But I can barely hear.
It is very spotty problem. There's mic on the ceiling.
I'm just trying to see how large is this on-chip memory is, because I couldn't find any spec about that.
I'm not 100% sure. I think it can be can differ between devices. If I recall, it's around like 2 megabytes. I'm not 100% sure, so don't take my word for it. But I think it's around 2 megabytes.
Okay. Okay.
I'd like to add that
Right.
on the hardware side, it's about 2 megabytes, and it's increasing with generations. But some of it is used also for other things internal to the firmware to optimize additional flows. So it can really depend on configuration. I think in the current version, it's about 256K available to the software, but it may change over generations.
Sorry, Yossi, how much of it did you say is available for the users?
Currently, I think it's 256 kilobyte. You can see it from IBV devinfo command.
And when this, so another quick question. So when you request for this memory with the UCP mem map, you're asking for an allocation mem map, and you pass a specific size, right?
Right. Yeah.
Right.
Okay.
We had an online question from Oscar. He asked, what was the maximum message rate that you achieved for process? It should have been graphed, and were you using PCI 4 or PCI 5?
PCI 4 or PCI 5? I don't know. I can check. It will take me a few minutes. And I can write it in the chat later.
So this, I think it's PCI 4. Which cluster was it, Roy? It was Jazz?
It was Jazz, yes.
Okay, so it's actually, it's PCI 3.
Any other questions?
And does this memory, when I'm using it in UCX, for instance, does it have to be used for atomic operations, or I can use it for something else as well?
You can use it for anything you want, but we can't guarantee that the performance will be better for any operation that you want. We know specifically that it will be better for atomics, but you can definitely use it for any RDMA operation.
All right.
But you cannot access it directly from the CPU, just like GPU memory, because there is no guarantee of memory semantics. So you can only target it by remote memory access.
Right, and with UCX, would it be like limited to a certain operations?
So you can pass it as a remote address and remote key for access operations, for any kind of remote access operation. But today we only have three of them, which is atomic, RDMA read, and RDMA write.
But I cannot pass it as a source buffer for any other operations.
You can also use it as a source buffer, but you cannot access that source buffer with CPU. So you cannot initialize it from the CPU load and store operation directly.
All right. Okay.
All right. If there's no other questions, let's give the presenter a quick hand.
Thanks.
Next up, we have Tom Gillis. So, do you want the mic?
I don't know if you can hear me.
Probably better save this words.
Okay. Yeah, thank you, and good afternoon, everybody. So today I wanted to present a bit what we have been doing over MPI RMA. And I think my main goal of today is really to come with a use case for RDMA write with immediate. And so that's the issue 2188. And so I think I should start by mentioning that I'm a bit late. So this is an issue that has been open in 2018, and Yiltan is late as well. But so over the last few weeks and months, we have been working over partition communication and RMA. And so I think we have converged with two different use cases. Yiltan has a very good paper. They just won an award for it at Cluster. And so I'm going to present MPI RMA use case. So the motivation of this talk is really to enable science. And so I think it's important to mention that. And so this is a picture of a simulation that's done by one of my former colleagues, Marion. And so it's a wind turbine. So they have like 3 blades. And they run this like over 72 hours, 1,000 of CPUs. And it's an old Fortran 90 code, and they don't want to change anything because, you know, it has been around for 20 plus years. And so they actually do science with that, and they do wind farms and stuff like that. And so their motivation with MPitch is really to enable them to like communicate efficiently across the scales in terms of physical scales, but also in terms of like computer scales. And so for them, there are like 2 different issues. The first one is the latency that you get, and the second one is the bandwidth. The bandwidth is their responsibility because they know the software better, and they know the algorithm better, but latency is really for us. And so when we look at MPI, and yeah, so this is a picture of Aurora, the infamous Aurora. And so my goal of today is to present different MPI implementation for MPI RMA, and then to give a use case for immediate data. So they did a study in 2019, and so the summary is that nobody is using one-sided, and everybody is using point-to-point, and even more people are using collectives. And I think it's a shame because one-sided is part of NVSHMEM, OpenSHMEM, and you also have point-to-point nickel if you want to play with that. And it's probably the most promising for GPU communications, and so it's really something that we are trying to push to our users, the one that are interested in moving to GPUs. And so there is a new addition to the standard in MPI 4, which is partition communication, and we don't really perceive this as like the biggest and the best solution for GPUs, and I can explain why later. So if we look at MPI RMA, so this is a very non-official version, so if don't tell the MPI police, they should be busy today by voting, so it's good. So just so that we are all on the same page, so MPI RMA, you don't have a sender and a receiver, you have a target and an origin, you open memory, you share it across targets, and then you can do some operations, so you can do MPI put and MPI get, you can do accumulate, fetch and op, and all the atomic operations that we just mentioned. And so for completion, you get an MPI put, and MPI put is our best hope of having very fast completion because you can just focus on local completion, and remote completion is more expensive because you get the network round trip. And MPI get on the other side, local completion, comes with remote completion. And so in MPI, you can enforce completion by synchronization. So you can use either passive or active synchronization. And the difference is mostly in the completion like semantics that you get. So if you use flush local or flush, so those two are like passive synchronization. And so at the origin, you get a local completion for flush local, a remote completion for flush, and then PSCW, so it's post-start complete wait, and that's the one I'm gonna talk about today. You get the semantics gives you a local completion on both sides, both at the origin and on the target. And then finally, the fence, nobody wants to use that. It's a collective operation. It's really bad, and I don't think we have any use case for this. So the idea is that we are trying to push our users to use PSCW. And the reason, because it looks really like send receive. So you open your memory, you register in memory, then you do post. So your target say, hey, look, I'm ready to receive whatever operation you want. The origin waits for that. And so we wait for the acknowledgement. And then after that, we do put. The network can be unordered. And so that's an important part of the performance that we get. And then we have complete wait. And so the question that we have been asking ourselves is what is the fastest way for synchronization? And the reason is that we really want to use this local completion. We don't want to care about remote completion, and we want to be as fast as possible, especially for users, and especially on GPU memory. So if we do that, the post start, so which is the initial acknowledgement there, it's optional, because sometimes you can get rid of it. If you have, for example, an old reduce, then you want to not do it. But so if we have to do it, MPitch is going to use active messaging. You can also use RDMA, and OpenMPI, I think, is going to use atomics, which is a weird choice, but why not? And then the complete wait that we get, which is so the closing acknowledgement, which is the important one, which is the one that's going to be expensive because you want to complete all the puts that you just did. It depends a bit what kind of tracking completion we have at the target. And so we have identified, and at least in OFI, and I'm sorry, I haven't used UCX yet, but so that's why I'm here today. We have identified 4 different completions that we can use. The first one is immediate data, so it's IB immediate data. In OFI, it's called CQ data, but it's exactly the same idea. Then we have remote counters, which are not supported in OFI for IB verbs. And so those 2 ones are very important because it makes the acknowledgement an optional. And it means that we don't really have to send a message once we are done with all the puts. We can, if we are smart enough, and if the user tells us, hey, I'm looking for X if I write on the other side, then because of the remote counters and because of the immediate data, we can just track that numbers and not acknowledge anything. And so we can save 1 latency. So those 2 ones are very important for us, and those are really where we expect performance. And then we have 3 others that where you need to send something. Like you need to send the closure something for it to be able to work. So the first one is fencing, and so that's you cannot use fencing NIB in the fabric, but so CXI has fence, and the API is available on CXI. Then we have write after write ordering, and that's something we just discussed earlier this morning. What is the semantics that you get and how you can get it. And so on IB, it's very cheap because the whole network is usually ordered. And so if you just stay in those like configuration, then you get write after write for free. And then we have remote completion, which is the worst, which is basically what we have been talking about also this morning. It's like you just wait for those write to complete, and then once they're all completed, then you send your acknowledgement, and that's what you expect to be the worst. And so it's also what we have in MPitch, and it's also one of the motivation of this work is to say, okay, let's make it better. Let's make MPitch a bit faster. So this is a summary of like all the implementations that I'm going to present today. So the first one is delivery complete. So it's this last, like where we wait for the completion and everything. It's great, it works all the time, it's very easy, every network supports it, but of course we have a delay when waiting for the completion. Then we have write after write ordering, and this one is a bit more challenging. So it usually works well with immediate data, but the problem is that you get possible ordering restriction, which is not always ideal. And also, if you have multiple endpoints, and that's an issue that has been mentioned as well this morning, if you have multiple endpoints, then you need to kind of close them all. And so you just multiply your latency by the number of messages you need to send. And that's not something we are really, that we really want to do. And then the last one is CQ data, so immediate data. Immediate data, it's amazing. The way I'm using it, it's just +1. So it's very easy. I just increment a counter. So it's just a simple bit that gets incremented on the target and just like counts the number of FI write that have completed on my target side. And then when I need to send this completion, so in MPI, PSCW, the user doesn't tell us like how many writes we are waiting for. So we just send, hey, I just did 10 writes. And then I just subtract that amount. And so whenever my counter reaches 0, then I know that I'm done. And I've just performed my 10 writes. And so the nice thing about it is that we can also have fast completion. And fast completion means that for some algorithmic reasons, because there is no reduce or anything, we can get rid of the initial synchronization. And then the complete wait can also disappear just because we use CQ data. And we can just track the number of completed calls on the targets. So if we put all that on, oh yeah, and so I think it's a good time to talk about partition communication and why we think it's not the best idea for GPU at least. And so if implemented in RMA, everybody keeps saying, hey, partition communication is amazing, it's great, it allows you to do whatever you want. And I think it's really close in design to PSCW, which is that you, ahead of time, you say, this is my buffer, so you register your memory, and then after that, once every partition is set, then you can just send them, and so it's easy. And then then on the target side, you get completion of your partitions. And so for those who don't know what a partition is, it's just your big memory that you just chunk, and then you can send those chunks independently. The problem is that we're given this slide, so all the different implementations that we can have on IB, is that we expect RMA to be really, really good when we can offset the synchronization that is needed by RMA. And so it means that you need many small messages. And it's not the best usage of your NIC and your network in sending many small messages to the same rank or to the same process on the other side. So what you're going to do, and that's what Yiltan did, and that's what he mentioned in his comments, is that you're going to aggregate your messages together in order to save latency. But so if you do that, then you decrease your number of messages. And so basically in partition communication, you will never reach this ideal state for RMA, which is I send as many messages as I want, and they are as small as I would like them to be. And so, and the API is really horrible when you start having like multiple different processes that you want to send to, because you need to register your memory multiple times, and then you need to do this acknowledgement with everybody, and so it doesn't really perform well. And so that's where really we think that PSCW is a stronger alternative to this PCOM, and that's why also we would like to open the floor for, and it's also part of a collaboration with Roie and Grant in Queens. We are trying a bit to compete and see who has the fastest implementation, PSCW or PCOM, and see what we can get. So if you want more details, we have a publication about that. Okay, so what I did in terms of MPI, and so it's not MPI because I did it on top of LibFabric, but so in terms of just to get you an idea, so I do a bunch of send, I do a bunch of receive, and this is my baseline. So this is what I'm going to compare to, and this is what I'm going to use to say, okay, is RMA faster or not? And then I have my RMA side, and so I have post start complete wait with a bunch of put. So I do that for n messages, and then I just wait for the completion. And so when I do fast completion, I don't take the start time into account, so the start goes up, and then in terms of timing, and the complete is actually just like a single. I changed the API a bit so that my target can say, hey, wait for X messages, and then I can just complete way faster. So I wanted to do that on Meluxina, but I have a MOFED issue. So if someone has an idea of how to solve that, I'm really happy to talk about it. So I didn't do it on Meluxina, I did it on Lucia, which is another system. It's the same GPU, it's the same network. They don't share the PCIe switch, which gives me very high latencies, like higher than what it should be. And also it was yesterday, so I haven't had time to really go through it again. So they don't share the same PCIe switch, but all the rest is the same. So I use LibFabric. I use the 1.20, so we just added HMM CUDA use GDR copy for the injection, so to not have 20 plus microseconds for latency when you inject, and then PMI, and then I use CUDA. right? So this is what I get. This is CPU. So CPU, I get my baseline, which is the point-to-point, which is this one. So that's the blue one. And then I switch from eager to rendezvous very early for GPU reasons. And so you can see I'm like way faster, and then all my RMA calls in pink, in green, and in orange are like way slower, and that's actually expected because I just need to exchange my messages and I need to synchronize and everything. So if I send a single message, RMA is gonna be super slow, and that's actually what you expect. I think it's already nice that we can see that delivery complete is the worst. Then on a single message, my CQ data is actually more expensive, slightly more expensive than the ordering. And I think the reason is just that we need to enter on the target side, we need to enter multiple times the CQ, and we get like 2 completion because we have the actual CQ data from the FI write, and then we get the acknowledgement using active messaging. And so that's more expensive than just using FI write and then using another FI write with empty and with a no length and just tracking that on the target. And so then after that, I can go to GPU. So GPU, we have some funky behavior for latency, but we are like very fast. So this is GPU aware. So the memory is just on the GPU. And then we get also like RMA, which is a bit higher. We have some, so this is my confidence intervals where you can see bars. I think it's 90%, so just to give you an idea. And then we don't really see a difference between CQ data and ordering, and I think that's also expected. So then we can increase the number of messages, so we can go to 64 messages. It's the same story, except that now the point-to-point is really slow, and the rendezvous behaves weirdly. We have, so delivery complete is the slowest, and then RMA is like almost able to compete with my point-to-point, and those 2 different approaches, CQ data and ordering, are basically the same. And then I go to GPU, and GPU it's just use RMA, right? If you have many small messages on a GPU, just use RMA and use CQ data or ordering and not delivery complete. And so I made those maps. Like this is where we see, like we can measure the ratio between point-to-point and put. And so when it's blue, it's slower. Point-to-point is slower. And when it's red, point-to-point, when it's blue, point-to-point is faster. And when it's red, RMA is faster. And so we have this transition because of the eager to rendezvous. It's the same that we see there. And so CQ data and order basically compare the same. So if you tell me, hey, we're not going to give you CQ data, I will be sad, but I could also use ordering. The problem is that when I go to GPU, I see an ordering that behaves better, like slightly better, which is what I expect. My CQ data is still performing weirdly, and I think it's also a question of protocols, and it's mostly point-to-point being weird than CQ data being weird. So another question is, can I go even faster, right? Like, can I remove my synchronization? And this is the fast completion I was mentioning before, is that we want to be, what is the fastest I can get? And so the fastest you can get is put plus signal and then signal weight in NVIDIA semantics on the other side. And so if you do that, then my ordering becomes bad, right? And the reason is because I know I'm sending 2 messages. And so I don't want ordering. What I want is CQ data, because then it gives me a simple FI write with some CQ data to track on the other side. And I'm like as fast, even on the CPU, I'm as fast as an injection that's been done in CPU memory. And if we compare on the GPU, it's even better. I have this weird like behavior when I decrease and increase again, and I have very high confidence interval, so I don't really know what's happening. But I think we can all agree to say that CQ data is the fastest, and then I get ordering, and then sometimes I get point-to-point, depending a bit on how expensive it is and depending on where your memory is and so on. And so the summary is basically, please give me CQ data. So this is data for CQ data. So CPU white, it doesn't really matter exactly what you do because we have this, CPU has already been very optimized and very fast, but when you go to GPU, CQ data is always faster than point-to-point. And so for users, it's really important because it means that if they want to use GPU, then what we're going to tell them is basically use PSCW with CQ data because UCX has just introduced that feature in the newest version. And so in conclusion, so what we tell our users is really that MPI RMA is the future of GPU to GPU communication. And we recommend usually, and I recommend usually PSCW, and the reason is that I have done the switch before. So you can go for send receive to PSCW very easily. You get very good performance. Don't use PCOM. It's really hard to implement, even on MPitch level. and send receive has been well optimized, but because of just semantics, you don't get as much as you do for PSCW. On the UCX and IB front end, we know that you can get ordering, and that would be useful. But what we really would like to see is this immediate data API that we could use, and both for flexibility when we don't really need it and it's not really faster, it's just more flexible because we can just, like, if you have multiple threads or different context or like different GPUs as mentioned this morning, you can just track or like order or like you can put flags to your FI write, and then you can just sort them on the other side. And so you don't need to care about multiple endpoints and all this stuff, because also you have like endpoints limitation. You just use CQ data. And so, yeah, I have an issue with Moffett. If you can help me, please feel free to reach out. And so, yeah, I hope really that in the future, UCX is going to ditch all this and is going to embrace immediate data. And so that's, I guess, my conclusion. And I would like to thank the MPitch team and then all the collaborators that have helped me in this work and acknowledge funding. And I'm very happy to take any question.
Seems like everybody loved it. So what is the challenge with your Moffett, Melnock software? You ask for help there.
Yeah, so I have issues in immediate data. So the completion of my immediate data on CPU memory violates the fact that the memory is ready. So when I get the completion, I read the memory immediately, and then the memory is garbage.
How is this possible? You have to follow that.
Something changing. He said it happens after.
When it happens again?
So in the newest version, so it used to work perfectly, and in the newest version, they have addressed the PCIe ordering issue. And what I see on the CPU and my memory CPU, I get the completion of my immediate data before my memory is actually like valid. And that happens for large messages.
Somebody enabled by default or what?
Enabled by default. Maybe flag gets enabled and maybe Fabric picks it up, or some other change more internal related to PC ordering.
You should talk with your.
Okay. Yeah, I mean, it might also be just Fabric that use, I don't know, something wrong or something weird, and that triggers something like an ordering issue. Yeah, so all that is from yesterday and Friday, so it was a bit of a surprise.
You can open tickets on, like, again, this is kind of not exactly UCX ticket, but you can open on UCX, I guess. You have a channel to redirect it to NVIDIA bug or whatever if there's problems.
I told him we should take it with the cluster vendor and escalate it for that channel.
Who is your cluster vendor? You know?
Yeah, Partek, the German stuff.
To get Intel in long support for that channel, rather than just asking on the phone.
I mean, yeah, I can just, the support seems a bit just to be in panic mode because they just did that update like a week ago. And I mean, it seems that it's only affecting immediate data. So I guess UCX should be fine, but yeah.
So regarding partition communication, do you see any use case where that could be?
I mean, my answer is just use PSCW, right? I can understand that the API is a bit hectic because you have those groups in PSCW that makes it scalable. And so maybe, I don't know. I think the biggest issue, so there are two issues. The first one is that you want to aggregate small messages, and that will basically reduce your performance. I mean, that would put you in a space where point-to-point is just faster because you don't have the synchronization that's needed. The second issue, and so a solution to that would be to allow each partition to go to a different rank. And so that would be just a window that you put that you give, and then you just write every like different chunks. So that would be one solution. And I think one of the use case, and so the other problem is threads. You want to use that with threads, but in MPage, we have no guarantee. When a partition is ready, partition number 3 is ready, we don't know which thread it is. Like, we have no idea. And it's really, really hard because then you need to lock everything, because just in case, because maybe I mean, you don't have a one-to-one relationship between a thread ID and a partition ID. And that's not ensured in the API. And so those are like the two tricky points. And so if you solve that, then I think partition communication is just a fancy semantics over PSCW, and then there is a value because maybe some users don't want to use PSCW because it's the first time you do that, it's kind of coming from a user perspective at least, and I was a user before. It's hard, right? Like, so, I mean, the first question is what the fuck is a memory model, and then it gets just harder and harder, right? So.
Any questions online?
So will we get CQ data or immediate data, you see?
We need to find the API thing. Maybe you can have some suggestion of which API you'd like to see. And where you think is the best place to edit, and we can take it from there.
Okay, sounds good. I think Yiltan did a comment about that. I think the send side is easy, right? You just add a flag or something. I think that the tricky part is on the target.
Can we connect it somehow to active messages?
Yeah, you can do that.
I mean, if you send something and it triggers active message handler, and active message handler would be able to see this immediate data. That'd be useful.
Yeah, I think that would be useful. It's a bit weird that it has to depend on active message, but.
So you're thinking of something like more similar to polling. We poll some queue and then you can get it.
So what there is in OFI, you have this single CQ that you get, and then you get an entry that's basically just the tag that has been sent from set from the origin. And I think the limitation on the size is not an issue because most of the cases 32-bit is more than enough. And especially if you just count the number of operations, you need 1 bit, right?
So it's different between Wi-Fi and here is Wi-Fi. I think it's mostly like CQ oriented, where you poll some things in order to get notification about things happening. CX is more callback oriented, where something gets called when an event happens.
Yeah, but we can attach a callback to any immediate data event, right? And then once you have that, then we can handle it from there.
I think it's similar to put with signal, like some suggested, right?
Yeah, it's exactly a put with signal. And so the immediate data is also, I think, would be useful for NVSHMEM and OpenSHMEM, because I think for the moment they are bound to this either disordering, and I think I've looked at the OpenSHMEM code, and so they just do 2 messages, right? They rely on ordering of the second one in order to be able to guarantee, and so Cool, thank you.
Let's thank the presenter. We have one more talk today from Akshay. If you're ready.
Akshay's online.
Can you all hear me?
There's quite a bit of noise coming through.
I see. Is this any better? Or is it just the same?
It's better.
And you can see my screen now, right?
Yeah, but it's not in presenter mode. You want to enter presenter mode.
Just a moment. Okay. Hi, everyone. My name is Akshay Venkatesh. I am a software engineer at NVIDIA. Today, I'll be presenting about UCX on Gracehopper. And a lot of this work has been done in collaboration with my colleagues at NVIDIA, the GPU communications team, and with a lot of support from the UCX core team. The outline for today's talk is a brief note about CUDA awareness in UCX. I'll provide a short overview of Gracehopper and talk about some of its unique features, and specifically go into details of what considerations UCX needs to make in order to take advantage of some of these features. So to start with, some of the GPU awareness in UCX is distributed over many different components. For transport and transfer related work, there's IPC transport that's used for intranode device-to-device transfers. And this basically takes advantage of CUDA's GPU, remote GPU mapping capability. And when NVLink is present, for instance, it can be used to take advantage of it. For the internode side, we have kernel modules like MVPMM or even DMMBuff that can be used to register memory with the NIC. Then subsequently, transports like IB can directly read and write from GPU memory. This is the scheme that's used for rendezvous transfers, and the zero copy transfers then are able to directly read and write from GPU memory. This is particularly important for the case where PCI bottlenecks are to be avoided, and it also avoids staging and associated latency. And there are still going to be cases where we are not going to be able to use zero copy operations provided by IPC or GPU Direct RDMA. And for those, we have GPU awareness through CUDA copy and GDR copy, which are transports that are used to copy between device and host memory. And these are used in either pipelining protocols or for eager protocols. We also have logic in UCM to basically be able to detect memory type. And this is needed for both transport selection and protocol selection. Memory detection also includes interception logic, which allows you to intercept alloc and free calls. And this is needed for safe deregistration of memory, which are used for zero copy transports. There is also topology awareness logic in UCS that we use for GPU NIC binding. Specifically, topology logic presents an estimate of bandwidth and latency between system devices. And we use this to query the nearest NIC to a given GPU. And we use that for zero copy operations, for instance. Without GPU NIC binding, the end-to-end latency and bandwidth is significantly impacted. So topology, UCS topology is a critical piece in that. And finally, we have UCP protocols V2, which is a framework that was worked on by the UCX core team to basically look at memory type and location in the decision of making optimal protocol selection. And prior to this, what we had was a common set of protocols and a common set of thresholds that were used for both host and device memory alike. And this led to poor performance for applications that had mixed memory workloads. Next, I'm going to talk about the Gracehopper superchip. Gracehopper combines an ARM Grace CPU with an NVIDIA Hopper GPU. One of the unique things about this chip is the presence of the NVLink C2C channel between the NIC, between the Grace CPU and Hopper GPU. This fabric realizes hardware consistency between the GPU and the CPU, and it also provides high bandwidth and low latency path between the two entities. The other unique thing about Grasshopper is the presence or the introduction of the NVLink network. This essentially allows for GPUs separated by the OS instance. Basically, two GPUs on two different nodes can now talk over NVLink fabric, and and it can support a connected domain of up to 256 GPUs. Lastly, another important feature that Grasshopper introduces is the extended GPU memory. For GPUs which want to oversubscribe physical memory that's provided by the GPU, Grace allows for extended GPU memory that can have CPU backings, and this can be accessed over a high bandwidth, low latency fabric like the NVLink C2C. And this can allow for certain workloads which stress GPU memory to be used. I'll talk more about this when we come to that section. For more references, please do refer to the white paper on this. It has much more details on Grasshopper. So the first thing I want to talk about is the unified memory feature on Grasshopper. Essentially, address translation service, ATS, allows the CPU and GPU to share a single per process page table. And this means that any memory that's allocated through malloc or POSIX memline or something equivalent can be accessed by both the GPU and the CPU alike. Prior to this, if the CPU tried to access memory allocated by the GPU, this would result in a seg fault, and vice versa. If the GPU tried to access any malloc memory, it would result in a seg fault. But ATS and the software equivalent HMM allows for the GPU and the CPU to access each other's memory. On top of that, the presence of NVLink C2C allows for this to happen in a very efficient manner. So firstly, page migrations are not a necessity, but and if things can move at the cache line granularities, NVLink supports that. But if the OS does dictate that based on certain access patterns, the pages do need to migrate and it makes sense to migrate, then migration is a possibility. And this migration has a specific effect, something for UCX to certainly consider, because UCX by default does pin memory prior to rendezvous transfers, and pinning is not necessarily desirable on Grasshopper because pinning will pin pages in place, and it may be the case that a GPU, several GPU threads are accessing memory allocated by malloc, and some pages ought to migrate, but pinning would prevent that. And without pinning, all these GPU threads would be accessing that memory location remotely. And ultimately, this can result in poor overall performance. And what we see is in UCX, both for intranode and internode, transports like IB and CMA do pin down memory before rendezvous transfers. And the solution we have thought of so far is to be able to detect platforms like Grasshopper and maybe even looking for even HMM systems, where when some sort of capability which allows pages to migrate between device and host exists. For instance, on Grasshopper, it's through hardware, a hardware realization, but on other systems, it could be through HMM. On such systems, it's better to opt for ODP style registration, where pages aren't pinned, but ODP allows for the NIC to still continue to access pages as they migrate. One of the caveats of this solution is that it only solves the internode problem, so we still have to think of a solution for the intranode. And the other thing to consider is when we realize that system allocated memory ought to be registered through ODP, it shouldn't be the case that all system allocated memory have to be registered with ODP. It's only the user memory that ought to be done. So the current status of this work is that we've started working on a PR that introduces something called migratable memory types. In this case, the memory domains populate a bit array with the different memory types that ought to be treated as migratable. Once marked as migratable, say for instance, if CUDA memory domain marks system allocatable memory as migratable, then other transports which are capable of non-blocking registration are exposed to this, and there they make a decision to use a non-pinning registration type like ODP for the specified memory types. The other extension that we are discussing is to UCP memmap, where in case users want to explicitly avoid any non-blocking registration for the memories that they intend to use with UCP, they can do so by specifying a flag. The last thing that we have to still consider is like the effect of prefetching policies. Currently, UCX does have some prefetching policies, but we have to see what the effects of this is on page migration and its effects on workloads running on Grace Hopper. At this point, I'll quickly stop and check to see if people have questions. If not, I'll move on to the next topic. And this concerns the NVLink switch system. This picture depicts the overview of an HGX Grace Hopper system. Here, what we see is Grace Hopper superchips are connected to this NVLink connected, NV-switched connected domain, where up to 256 such nodes can be connected to an NVLink switch system. For other networking purposes, there's also Bluefield DPUs or ConnectX-7 NICs that are attached on the same node, and they are interconnected by a quantum to InfiniBand switch. For GPUs that have access to other GPUs over the NVLink switch system, CUDA exposes API to allocate memory that provides GPUs across nodes to access each other's memory through IPC capabilities. And this is through the extension of CUDA's already existing virtual memory API. One of the takeaways from this is that we have import-export capability in CUDA IPC transport today for similar capabilities between GPUs within a node. But to extend this to work across nodes, we effectively have to promote CUDA IPC transport, which today is an SHM device, to a net device. And this comes at changing certain capabilities in CUDA IPC. This includes things like connection establishment logic, reachability logic, and also keep alive feature logic. The other thing here is that once we do this, CUDA IPC now becomes a capability for internode transfers. And so when there are two competing transports, such as IB and CUDA IPC, are competing for a transport for internode device-to-device transfers, we have to make the right call depending on the reachability conditions. We have an initial prototype with this that we were able to work on with the help of UCX core team, which allowed us to relax some of the keep alive requirements. And with that, we see full saturation at large messages for two GPUs on two different nodes. One of the things you will notice here is that the point at which we saturate the available bandwidth is at like 16 megabytes. And that's because for the bring up machines we're using today, we use a TCP control exchange plane. But with a slightly better control exchange plane with a shorter latency, we should expect this curve to move further to the shorter message range, as it is the case with CUDA IPC intranode transfers today. The workaround is being worked on by the UCX core team, and we may discuss more about this at the end of this talk. Any questions at this point? Okay, if not, talking about the last feature, this is the extended GPU memory. And as I mentioned, Grasshopper exposes this capability where GPUs are allowed to access system memory as though they're CUDA allocations. And the backing memory resides on CPU memory. And this CPU memory is significantly larger than what's available on the GPU itself. And for these extensions, all transfers to CPU memory go over the NVLink C2C, which has very high bandwidth. But not only this, with this capability, a GPU can access not only local CPU memory, but also remote CPU memory over the NVLink network. And effectively, this allows for up to 150 terabytes of memory for a 256 GPU NV switch connected domain. GPUs will access, depending on the paths to these different backing storage, for memory that resides on local CPU, it'll just involve using the local C2C link. For memory that is on remote GPU, it would require us to traverse over potentially one or more switches and then over to the remote GPU. And if the backing memory resides on remote CPU, then you'd have the additional remote NVLink path as well. One of the implications of using extended GPU memory, EGM, on UCX is that for CUDA IPC to be used for these, CUDA IPC would have to support accessing and registering system memory. And this means that CUDA IPC then becomes a candidate for internode transfers for system memory as well. And it may not be the capable, as this sort of extended GPU memory requires a special allocation. Not all system memory can take advantage of NVLink. And for appropriate cases, the expectation is that CUDA IPC registration fails. And when such a thing fails, we expect UCP protocols V2 to fall back to what is the next best transport, which would most likely be IB. And for this, we require APIs like ARCI and PAC to fail, and UCP Proto V2 to gracefully handle these failures. And a note that the same sort of fallback mechanism is expected for GPUs not within the NVLink connected domain, and a failure would result in IB being picked for internode device-to-device transfers in such cases as well. And before I move on to the last of the requests, I want to again check if people have questions. Okay. If not, the last set of things I want to discuss are some requests for the UCX core team, essentially in light of what is coming in the future with CUDA. CUDA is expected to soon introduce API to query physical locations backing user pages. And this is required whenever we have to exercise pipeline protocols, where today UCP protocols V2 is only capable of using host bounce buffers. But if we know on Grasshopper what are the physical locations backing each of the pages, then it may be beneficial to use bounce buffers closer to each of those pages. And for that to be realized, protocols V2 essentially need to have a notion of performing estimates with use of device bounce buffers and EGM bounce buffers as well. So this is a request that we have for this upcoming feature. At this point, I want to check with, say, Yossi or others from the UCX core team if they have thoughts on this.
Actually, device memory pipeline is in the plans.
Okay. Yeah. So one thing I do want to note is that like, and I expect this to be generic when you say device bound memory pipeline. We want to be able to use not just device bounds buffers, but potentially EGM bounds buffers as well, as we see use cases for within the node. So Yossi, is my expectation right that it would just be generic?
Would they have a different sys device?
Yes, they would have different system devices, and they would have associated different latency and bandwidth as well.
I think, yeah, today we have the infrastructure for this. The hash table that you added, the key system device and value is the memory pool.
Okay. The other question is open. So as I mentioned earlier, ODP suffices for internode transfers between grace hoppers, but within the node, we still are currently using CMA, and CMA or equivalent is known to use pinning before rendezvous transfers. Now, we can use a pipeline here too for two grace sockets within a node to basically go over NVLink through the C2C channel, and it would result in a higher bandwidth. But one of the problems with this is that because we are pipelining, we're essentially going to introduce copies that may result in page migrations, because on the receiver side, say we're using device bounds buffers, then basically we have the copy engine performing writes into GPU memory, into user GPU memory, or into user CPU memory. And this can trigger, because of access patterns, this can trigger page migrations again. And one of the primary goals of using ODP was to leave user pages where they reside and not have the communication library trigger any sort of migrations. But use of CMA or use of a pipeline scheme would still result in potentially having migrations, undesirable migrations. So we need a scheme. So an open question here is like, can we think of anything other than also using ODP for intranode transfers, or do you potentially see an equivalent of CMA that prevents any migrations?
So let's say that we have a way to disable CMA. If we somehow say that CMA is not a qualified transport because it would be in something that is not looking, then the next best thing would be the XPMA. XPMA, I think, is also being things. So what would you say the best way to transfer such buffer would be?
This is an open question. Like I mentioned the pipeline scheme that has page migration effects as well. So I was wanting to check if there are any other non-kernel methods to avoid page migrations. But as you mentioned, XPMM also has the same effect. It allows for you to attach remote memory, but you still have to perform these copies. And these copies can then result in page migrations that are undesirable.
So it's either copy or zero copy. Zero copy means something like RDMA with ODP.
Right.
Or copy with something. But something probably, if it's something CPU based, it would be in it. So that something has to be GPU based. Maybe the question is if it's really value for copying things through GPU mechanisms. But it really break on the page migration state that we want to preserve.
Yeah, so we've only tested through some micro benchmarks, and those are not good enough to indicate as of now. But I think some workload analysis is pending for that to see what are the end page migration effects. for now, I think one of the options we would like to have is potentially to, automatically disable CMA if we detect grasshopper. And that's something we can work on a PR.
I think that the direction would be to somehow say that CMA is not applicable to memory types that were registered with non-blocking.
Right, right.
Like we said that we cannot bin or we cannot register with any transport that doesn't support non-blocking registration. We should maybe also say that we cannot zero copy transfer with any transport that also does not support non-blocking.
Well, that seems like a reasonable approach. Okay. The last thing I had was about prefetching policies that or ODP exercises today. And I wanted to consider the implications of those on grasshopper. So what I'm curious to know, like, what are the current default prefetching policies that UCX uses with ODP?
So there is option on UCTIV level to prefetch memory of ODP when we register it. We don't have prefetch on the in RDMA operation, for example. We considered saying that before we start a zero copy operation, instead of registered memory, what we do today, the memory registration will just do prefetch instead of actual registration.
But on prefetch, do you think that would have the effect of migration? Say if it was on some other NUMA today, right? Like you have two NUMA nodes, and you have a NIC that is, issues a prefetch operation with affinity to another NUMA node. Would that result in page migrations? Because we can expect the same sort of migrations to occur on grasshopper as well.
It shouldn't have migration. I think that it just queries where the pages are. It should at least query where the pages are at that point and populate the translation tables.
Okay. Yeah, I think the other studies pending there for us to see if prefetch has any undesirable consequences. But that's something that we'd want to understand before implementing certain policies in UCX for grasshopper. Okay, that's my talk. Are there any other questions?
When do you think we'll have all the goodness in upstream?
So a fair bit of this is already in place. So for instance, the DMA buff work and ODP work, like some of the foundational work is already in place. The PR that we're working on to introduce migratable mem types to allow grasshopper to automatically choose ODP as a candidate for certain user memory types, that we should expect by next release, like say closer to March timeframe. And we also expect we have a more or less working prototype for use of multi-node NVLink features, and we should be able to target that as soon as the feature becomes fully public.
Thank you.
Go ahead.
No.
I have a more general grasshopper question. If you have a NVLink connected domain, do you have always single operating system that manages the whole domain, or you can have like operating system for nodes and manage them that way?
Yes, so they are, each of the nodes have their own operating system. It's just the fact that a group of GPUs now belong to what is called an NVLink connected domain, and only within this subset of GPUs can they talk to each other. And this is currently limited to 256 GPUs. But each of the GPUs can reside on separating operating systems. There's no requirement that all of the GPUs within this NVLink connected domain be under the same operating system. I hope I understood your question right.
Yeah, yeah. Thanks.
Okay. You see, before we finish, like the one thing that I kind of brought up was Archie unpack failing, leading to Proto-V to gracefully falling back to the next best transport. Internally we had discussed that, and I don't know if you had a specific time frame in mind for that feature.
Actually, according to our discussion, I think we said it should work today already because we have the memory domain map for the Archie unpack. If something failed to unpack, should select the protocol among the others that were available.
Okay, okay, that's really good to know. That's that. Okay, thanks everyone.
Gilad, got to close for.
Take a picture? We need to take picture. We need to take a picture.
Take a picture right after this.
Take picture, and then Pasha can summarize it there. So you want to take picture here in the front, or?
I think in the back because of I think light here. We can try in the front.
Okay.
And camera. Yeah, I can take picture.
Yeah. No, we need someone else. So you need to be the picture. So do you have any victim from the outside that can take a picture?
We can try to.
I'll see if I can get someone to take a picture for us. All right. I guess we can bid farewell to the virtual audience.
Yeah.
Okay, so let's do closing notes.
Yeah, do closing.
So I want to thank again all the presenters today for excellent presentation. It's very technical, very exciting, a lot of cool work going on. Please join tomorrow and day after tomorrow. We still have plenty of agenda for every day. We will start around the same time. Hopefully no technical issues this time around. And again, thank you guys for attending today, for joining online, and I know a lot of people from Europe and Israel joined, so thank you for staying online so late. Really appreciate it.
And thank John again for hosting.
And yeah, John did excellent. After lunch, we have kind of double send him. So yeah, thank you again for hosting us, and it's really fantastic. And thank you, Aaron, for sponsoring this.
Tomorrow.
Okay, see you tomorrow.